Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 27, 2025, just yesterday. The standout result is a practical, data-guided, gradient-free way to merge multiple expert language models that consistently beats common baselines while converging in only a handful of optimization steps. The paper is titled PSO-Merging, Merging Models Based on Particle Swarm Optimization, and as we will see, the implications for scalable multitask modeling are quite significant. In short, the method adapts particle swarm optimization, seeds the swarm with experts and sparsified experts, and delivers fast, memory-efficient merging across several model families. On X, a post praises particle swarm optimization for model merging, noting strong results and a surprising boost from sparsified experts, and it calls the work cool. Engagement looks solid with about 127 likes. Alright, the previous segment outlined the motivation and setup. Figure 1 shows the PSO-Merging workflow, which starts with initialization, where the swarm includes the pre-trained model, each expert, and their sparsified versions, so the search covers diverse directions while reducing conflicts. The iterative loop then evaluates fitness on validation tasks, computes velocities guided by personal best and global best, and steps through parameter space. The process converges to the global best particle, which becomes the merged model. So the previous figure laid out the workflow. Table 1 reports multitask results on FLAN T5 base across 8 glue tasks, and the bottom row shows the headline. PSO-Merging achieves the best average, 81.24. The gains come mainly from strong MNLI and MRPC, which read 83.80 and 80.64, while staying competitive on the rest. Evo peaks on SST2, but its average lags because QQP drops sharply. The message is consistent performance that lifts the overall score. Okay, the previous figure highlighted gains on glue. Table 2 compares larger families across 3 experts, and the averages tell the story. PSO-Merging tops Llama 213B with 56.82, leads Llama 38B with 61.12, and wins Mistral 7B with 55.35. The strength comes from balanced scores, because GSM 8K and MBPP do not trade off sharply. Ties sometimes spikes on MBPP, and Evo peaks on GSM 8K, yet their overall averages trail. While the previous table compared large model families. Figure 2 shows how particle scores evolved on the optimization set, as the momentum coefficient W changed, which controls how much a particle keeps its previous velocity. With W equal to 0.2, all particles climbed to similarly high scores, so convergence looked stable. With W at 0 or higher than 0.2, several particles stalled or even collapsed, especially at 0.8 and 1.0. The takeaway is that setting W near 0.2 stabilizes search without freezing or overshooting. Alright, the previous figure highlighted the role of momentum. Table 3 presents 4 task results on Llama 38B, and the headline is clear. PSO-Merging delivers the highest average, 64.47. The method posts 80.89 on Alpaca Eval and 50.60 on MBPP, while staying competitive on GSM 8K and PSI-Q, which keeps the overall average strong. Evo edges PSI-Q with 82.90, but its average ties below because other tasks dip. Wrapping up, 2 takeaways stand out. PSO-Merging offers a fast, gradient-free path to multitask models that beats common baselines, and sparsified expert initialization reduces parameter conflicts while keeping memory near inference-only levels. The broader implication is practical, scalable merging for shared base models across tasks. That is it for this episode of the AI Research Roundup. I am Alex, thanks for listening.